scale, but 3-point loads off of this truss, 200 pounds, 400 pounds, 700 pounds. Okay, pin connection here, roller connection here. Okay. Now, what was my question here? Okay, so we want to find the forces in BC and EF. Sorry. BC, which is this, and EF, which is this. Okay. Okay, so how do we do it? Hopefully the truss doesn't throw you off, even though it's skewed. It's still the same exact way. Everything is handled the same way. So I want to find reactions, right? So how do I find reactions? We know we have two reactions here, one reaction here because it's a roller. Everything in this direction is 0 over there, right? So what do? Some force is about a point, some force is about A or D, some force is about A. Okay, so what are my dimensions? How do I handle these forces? How do I handle this 400-pound force around A? Yeah.
4 times 400.
Okay, 400 pounds times 4 feet, all right? 700 pounds
Times 8.
times 8. The 200 pounds, this one, times what? 8. What else?
Minus,
Yeah, minus D times 12 feet. Okay, what's D? Got it? What? What's the math? Don't use your phones on the exam, right? Come on, so if this was a problem on the exam, I'd give you points for finding the reactions, and I'd give you points for finding the members. So if you couldn't find reactions, you lose all the points, right? So if you get the reactions right, at least you get partial credit. So what's D? Do the math. What? All right, now how do you find the other reaction? Okay. So what do I have? I'm looking for AY. So AY plus 733. There's only two forces that are going up. Minus what? What? 200 minus 700 minus 400. So what's AY? Yeah. Okay, so these are reactions, 733, 566.67. Do I have anything in the horizontal direction?
AX.
What? I got AX. What's it equal to? What? Yeah. Okay, so I get these two reactions. Now I want to find these members. Now, you can do it any way you want. You can start method of joints. You can start from any one of these points and calculate what that would be. I chose to do method of sections. If I went through here, I cut through this member and I cut through this member. And consequently, I cut through this member. So that's my section cut. And if I treat this as the analysis portion of the problem, I'm going to rewrite this thing. So what does it look like? I end up with this triangle with a force, and a force. Okay, so this is A, B, and F. Is that F? All right, so that's my section cut right here. And those are the forces that I'm exposing, or I'm representing by removing the member and putting the force back. All right, now these directions are just arbitrary. We don't care. They're just a placeholder. I may be going the wrong direction with them, but I don't care. And so BC is this member right here, right, BC. So how do I calculate BC?
The moment around F.
What?
The moment around F.
Yeah, moment around F is probably the easiest thing to do. Right? So how do I do that? What do I need in order to do that? I have 5.67 is how far away from F? What's the perpendicular distance? 4. Right? Okay, that's easy enough. What's the perpendicular distance for BC? It's this, right? So I need to calculate this. So how do I calculate that? So that's the way I did it, but, you know, I don't care. You can do it any way you want. Basically, I'm just looking for this length here, so I need to know what's happening. And I'm just calculating the angle, 36.87, 3/4, using, you know, law of sines, and I'm calculating the length B to be 2.4. I mean, you can do it any way you want, I don't really care. It's just, how do you figure out what this is, right? You have these lengths. You have 4 feet, you have 3 feet, right? So you want that. You want that distance. All right, so you could figure out what one angle is here, right? And then you can figure out what's happening. So, there's going to be some trigonometry involved. But, so now how do you get, so you take your moments around F. Okay, putting yourself at F, you have the 566.67 running, spinning this way, and then you have BC spinning this way, right? So, that's some of the forces around F. Times 4 feet plus BC times 2.4 feet equal to 0. BC is equal to a negative 444.45. So the negative sign tells me that I've chosen the wrong direction, so it's actually going like that. And if it's going towards the joint, it's compression or tension? Compression. So that's what you got. So the only thing that, finding the reaction should be pretty straightforward. Doesn't matter what it looks like. The reactions are always going to be done pretty similarly, the same way. The only thing that caused you to pause a little bit was finding the perpendicular distance. If you didn't like finding that perpendicular distance, you could have taken the component of this, find the angle here, theta, take this component and that component. This component would go through F, and then you just left with that component times the 3. Right, you can do that too. It's up to you and how you did it, or how you would like to do it, and you should always check it, right? So just remember, every time you're solving something, there's always another way of doing it, and hopefully you recognize that, and you can use that as a checks and balance, and you can make sure that you are, at least your numbers are coming up right. It's easy to make a mistake. It's easy to forget a negative sign and think that this is in compression or tension rather than compression. So you have to kind of slow down and review what you're doing. I'm going to send you this example for the truss. This was actually off of a final. So I'll send you this one along with another one to look at as an example. And so the trusses is a culmination of perhaps most of what we've been discussing in the midterm, because it comes together with everything. But we also want to look at all the other individuals. We want to figure out, I want to look at what beams are doing and the moments, and I just want to run through what we want to make sure we cover for the midterm. All right, for the trusses, you're going to have method of joints and method of sections, right? That's the analysis part. To find the forces in the truss, but you still have to find reactions. We still want to be responsible for simple systems like All right, this is done the same way a truss is done. We would take this free body diagram and take this joint and figure out what the tension is in the cable here and what the compression is in the strut. So you're doing exactly the same thing in trusses with method of joints. You're doing the same thing. You find your reactions, and you're finding what's going on in the individual elements. In this case, we start from here. We start from the joint, because I can't tell you what the reactions are until I know what's happening with the members. I don't have dimensions, so all I have is the angle, right? So here is 40 degrees, and this is 30 degrees. So this would be 30 degrees. So if I don't have the lengths or anything, I need to start with the forces here. So I break this up, some of the forces in vertical, some forces are horizontal, and we solve for it, right? You're going to have two equations, and then you want to solve for the two unknowns. So if I was to break this up, if I was to look at node A, let's say, all right, and I have 30 kips. 40, 45, sorry. So I'm looking at this compression element first, right? And then I'm looking at so I want to add all this together, right? Keeping it separate. This is at A, this is at A, this is the compression, this is the strut, and this is the cable. So you're going to summarize all the forces in the vertical, all the forces in the horizontal. You have two equations, and we'll have an unknown AB and an unknown AC, and you can solve for them. All right, we've done that a couple of times, or more than a couple of times. All right, so this is a built-up section, and we want to find the center of gravity. Okay, we want to find that center of gravity for the composite section. So what I'm looking for is basically what the distance is nothing there. Somewhere towards the top, we're going to have this balancing point, this center of gravity, where this thing, I can spin it around and it would be balanced. If it was floating in space and there was no gravity on it, and I were to spin it, it would spin around that center. That'd be a center of gravity. So what am I doing? I'm giving you the components. And we want to locate where that center of gravity would be. So if I did this problem over here, y bar is equal to all right, this again is the sum of the areas times the individual center of gravity or the centroid divided by the total area. So this is this equation which is the same as right, the resultant times the y bar times the area times its center of gravity. So doing this problem kind of like in table format is probably the easiest. All right, this is a 2 by 26. Sorry, this is 26 inches. The 8 by 8 by 1 inch angle, and the 2 by 17 inch plate. All right, so this is 1, this is 2, and then this is 3. So the area of the 2 by 26 inch plate, if this is 2 inches and this is 26 inches, what's my area? Yeah, 52 square inches. And what's y bar? If I was to take the center of this down to here, what is it? Hmm?
9,
This is 17 inches, right?
19,
Yeah, 19.
18.
18. Right, so 17 plus 1 is equal to 18 inches. Okay? The 8 by 8 by 1 angle is a rolled section, meaning I bought it or it comes milled like this, right? And the properties of an 8 by 8 angle is that it's, for the dimensions, it's 8 inches by 8 inches. It's got a center of gravity that's out here somewhere. Y bar and X bar happen to be the same, right? But the area is 15 inches, and the X bar and the Y bar for each one of those is 2.37 inches. So if I gave you this with that information, hopefully you could supplement this and put it into here. So the area of the 8 by 8 plate is what? we have two of them, so it's 2 times 15. So, and then what's y bar? Y bar is over here, right? So it's,
14.16.
what is it?
14.16.
Yeah, so how'd you do it?
17 minus the 2.
Exactly. 17, 17 minus 2.37 inches equals 14.63 inches. Exactly. If there's any trick to this or difficult part, it's that. It's coming up with, this is upside down, so you have to imagine it upside down and know what you're looking for. The 2 by 17 inch plate, how many inches is that? Square inches? 34. So let's add that all up. That's 116 inches squared. What's the y bar for this 2 by 17 inch plate?
8.5.
8.5. All right. All right. So this is 8.5. Okay. So I need to, I need another column here. This is my AY. All right, so I have to multiply this times this, gives me what?
936.
936, right? And what are the units? This is inches, and this is inches squared, inches cubed. Okay, 30 times this. Yep. Okay. 289. Getting there. Okay, I have to sum this up, and that's equal to, I got 1663.9. I think that's right. So then my equation, y bar is equal to the summation of A times Y over the total area is 116 inches squared, gives me what?
14.34.
34 inches, right? This goes away, that goes away. So that's it. So my y bar then okay. So that's how we found the center of gravity of that shape. So it's best to, know where this comes from, but know this equation, or just look it in your notes, you'll find it. It's always the same thing. What would x bar be? Right down the middle, because it's symmetrical, right? So that shouldn't be a problem, right? So if there was a trick, it was this. It was taking this information that I supplemented, and you had to work it into the problem. But the mechanics stay the same.
Are these three numbers given?
I would give you that. In that case, yeah. I would give you everything. I'd give you the size of everything. And if I call this out an 8 by 8 by 1 angle, I would give you that information. That is a piece that you would buy, from a catalog, or you would order it. And so we would have its specific dimensions. You wouldn't have to calculate it, right? You had a question? No. All right. Okay. So, in this problem, again, I'm looking for all the stuff that we know how to do. I'm looking for our reactions. And I want to know what's happening maybe at a point on the beam. I have this cable that's coming down. So this is a linked system, right? So in order to solve the system, the easiest way to do it is separate it. If I pull this system out and then normalize the vector here, I can solve everything associated with this, assuming it's in equilibrium. Then I can trace back and find the reactions at D. So your free body diagram is the whole problem, really. Okay, this is broken up into two vectors. This cable is broken up into two vectors. This uniform load is broken up into point load, right? So in this case, this point load is equal to 12 feet times 3 kips per foot. So I could put it right at the center of that point load, which is 6 feet away, right? This vector here is what? If this is 60 degrees, and this is 60 degrees, then this vector is what? It's BD
Cosine.
cosine 60. And this? Okay? So I can calculate what's happening here. I can find my reaction at C based on my 20 kips. All right, I can find some of the forces, or use some of the forces in the vertical to find Cy. I can use some of the forces in the x direction to find what?
CX.
Cx. All right, then I could take whatever I find here as BD, plug it back in here, find my reactions. I just want to, this link system, we're going to do something like that on the test. I'll send you this review to go over, but it's pretty straightforward. It's all the same stuff. A beam problem, we want to look at least one beam problem. All right, so all this is a bookkeeping type of problem. I have a beam, I have two cantilevers, this is pinned, right? This is on roller. We don't have any forces in the x direction, so anything in the x direction, 0. So all you're being tested on here is how do you keep track of your forces. So if you want to find reactions, I'm dealing with 1, 2, 3, 4, 5, 6 loads on this beam. So all it is a bookkeeping type of thing. I find reactions around A, All it is just keeping track of what's going around A counterclockwise or clockwise and counterclockwise. So the 10 kips is going around A clockwise at a distance 5 feet away. The other 10 kips is going around clockwise at 15 kips, right? What's happened with that point load? Point load is, or the uniform load, is equivalent to this point load, which is 4 kips times 10, which is 40 kips. And how far away is that? 5 plus the center of this thing, right, is 10. So what's the distance away from A? 10. All right? So I've accounted for 1, 2, 3. What about this 20 kip? How far away is that from A?
24.
24. What about B? Which way is it going?
Minus.
What did I forget? Right? This minus 20 kips is going this way 8 feet. So all that is just a bookkeeping problem. But if you could do it, all it is just keeping track of all your forces going around which way. And I can solve for B and I can solve for A. You could get B is whatever, and some of the forces in a vertical direction, you can find A. I think we've done that so many times by now. And if I asked you to find the moment at, let's see, somewhere along the beam, what would you do? So if I asked you to find a moment dead center here, how would you do it? What?
What's the question again?
If I asked you to find the moment at C, how would you find that?
You could just do anything to the left or anything.
Exactly. Put yourself here, look to the right and solve the moments, or look to the left, solve the moments. You're going to get the same exact number one side as the other side, right? They're going to cancel each other out, you'll have 0. So if I ask you for the moment along the beam somewhere, you could quickly figure that out. So I think, in general terms, I've covered all the topics we're going to talk about. If we can do that, we can, we have a truss problem, we'll have a cable problem, we'll have a linked system, we'll have a beam problem, we'll have a center of gravity problem. So it's probably going to be 5 problems. And shouldn't be any tricks. It shouldn't be thought of as any tricks. I'm not trying to trick you. I'm just trying to get you to take all the concepts we learned, equilibrium and static understanding, and apply it to these structures, right? And that's all we do. All right, so like I said, I'll send you review notes, and I'll send you some example problems. I think I've sent you a couple of midterm tests without solutions. I'll send you some with solutions. So you got to put a little time in and you got to study for it, because if you're familiar with it, it should be really simple to do, and you'll spend most of your time just checking, writing it out, and then come back checking. So prepare yourself for it. You can bring anything you want into the exam, except a computer and a phone. You can bring your calculator in, you can bring your books in, your notes in, solve problems, I don't care. But I don't want your phones, I don't want people taking pictures and sending it to other people, because then I'll get papers that wrong answer exactly the same way, several people. So we don't want to do that. And make sure you have batteries in your calculator, because that's happened too. People run out of battery and they don't have a calculator and they try to do it by hand. And that's just more of a problem. And know how to use your calculator. A lot of people think think they could just use the calculator for the first time on the exam, and then they don't know how to use their sign functions, and it's a problem. You know, again, it's not supposed to be a very difficult test, but it's going to take 2 hours of your time to solve it. All right? That's, yep.
I just want to reiterate with you, what's the date and time of everything?
Yeah, I sent it to you in an email, but it's the 20th. It's Friday, next Friday. It's at 8 o'clock, room 107, and from 8 to roughly 10:10, because we have to be out for a 10:15 class, I think. All right?